Hi, my name is Rodolfo Manacho, and I'll be going to report to you the topic regarding QR decomposition, particularly using the Gram-Schmidt method or the Gram-Schmidt process. So for this lesson, for the QR decomposition, there are actually three known methods or process wherein we can solve for the QR decomposition. First is using the Gram-Schmidt process. And then second is using the household reflection. And then the third one, we have to use the given dimension. So out of this three topic, I'll be focusing only on the Gram-Schmidt process because it is actually has something to do with linear algebra. Unlike the other two, it has something to do with the trigonometric functions. So we will be using the Gram-Schmidt process for the entire duration of this discussion. So first, we have to know what are the objectives of solving the Gram-Schmidt process. So the first one is to find an orthogonal basis. So what is an orthogonal basis? So from what we have learned from our previous discussions, orthogonal basis is actually, in other words, it is perpendicular. Okay, it must be perpendicular to a particular base. So before we can have a particular base, we have to solve first for the normal vector. And that is the second objective of the Gram-Schmidt process. Again, the first objective is to find an orthogonal basis, while the second one is to find the orthonormal basis. So for the QR decomposition, A is equals to QR, where Q is an orthogonal matrix and R is an upper triangular matrix. So by the way, this is just an overview for the QR decomposition. Okay, later on we will be focusing only on the Gram-Schmidt method. So the QR decomposition of a matrix is a decomposition of the matrix in an orthogonal matrix and triangular matrix. That's what I've said a while ago, where QT times Q is also equivalent to I, or the identity matrix. Easily. Q transpose is the transpose of Q and I is the identity matrix. So later on we will see how this goes with our discussion. Gram-Schmidt process is a process in which we are looking for the orthonormal basis again. If you can recall the objective, the orthonormal basis, and then we also just need to find the normalized vector. That is the second objective. So normalizing a vector means to change it so that it points in same direction. Okay, the main reason we use normal vector is to represent a direction. For example, if you are modeling a light source that is infinite distance away, let us say at this the light source of the star that reaches the earth. So you can't give precise coordinate for it, but you can indicate where to find it from a particular point by using a normal vector. So this is obviously true, and this is actually one of the practical application of the Gram-Schmidt process. So to find an orthogonal basis found by sets of vector as well as the orthonormal basis, we have to look for the, again, orthogonal basis and the orthonormal basis. So we'll be solving this example, x of 1, which is comprises by 2, negative 5, and 1, and then x of 2 comprised of the components 4, negative 1, and 2. So as you can see, we only have here two vectors. So we will be using formulas here. So these are the formulas that we'll be using. V sub 1 is equals to x sub 1. Why we equate this one? Because our x sub 1 will be our main vector or our reference vector. So for vector 2 is equals to x sub 2 minus the product of x sub 2 and then the projection of v sub 1, which is also similar to x of 2, the quotient of the cross product of x sub 2 and v sub 1 over v sub 1 cross product of v sub 1 multiplied to v sub 1. So I will not be focusing on the discussion on how we get this formula because it is just the formula here. However, I will not use this formula. I will use this second one formula so that we will have a shorter solution. Anyway, we already know how that product of matrix or vectors does, so we will use this one. Okay, so v sub 2 is equals to x sub 2 minus the transpose of x sub 2 times v sub 1 divided by the transpose of v sub 1 times v sub 1 Okay, this quantity will be multiplied to our base of 1. So, for example, if you are also solving for 3 vectors, you can use this formula. So, in this example, I'll be using only the 2 vectors. So, we only have to use the V1 and then the V2 formula. Okay, so let us proceed with our example. So, we have to solve this one, and I'll be showing you a video on how to solve this example.
Okay, so we have here the problem, okay, as an example. So the problem says we have to find an orthogonal basis spanned by sets of vectors as well as the orthonormal basis, where x of 1 is equals to 2, 5, 1, and then x of 2 is equals to 4, negative 1, and 2. So by just looking on the problem, we have to solve two things here. First is we have to look for the orthogonal basis, and then after we get the orthogonal basis, since we are looking for the orthogonal basis of our x of 2, that will be our base of 2, and then after that we can solve already for the orthonormal basis. So since we are using x of 1 as our reference, we will equate x of 1, which will be equal to base of 1. Why? Because this is our reference vector. Okay, so we are looking for the orthogonal basis and then orthonormal basis of a vector in reference to our x of 1. So we already have here our first formula, which I have posted on our presentation, on our slide presentation. So now we will be looking for our v sub 2, and then the v sub 2 formula, which will be which is already posted a while ago on the screen. So our v sub 2 is equal to x of 2 minus x of 2 times the dot product of v sub 1 over v sub 2, v sub 1 dot product of v sub 1, and then this quantity will be multiplied to our v of 1. So as you can see here, we are using dot product of these two references, or these two components, x of 2 and then v of 1. However, if we will use this formula, it will require a longer solution. So let us use this one, since we already know that doing the dot product is also similar to making a transpose of this component. So we will rewrite the formula as x of 2 minus x of 2. Instead of putting that product, we will use the transpose times v sub 1. Okay, same with the denominator, v sub 1 transpose. Okay, again, instead of using dot product, we will use transpose, so that we will have a shorter solution. V sub 1 transpose times v sub 1 times the v of 1. Okay, now we already have here our formula. The next thing that we need to do is substitute everything using the given values here, x of 1 and x of 2. Again, our x of 1 will be equal to our our v of 1 is equal to our x of 1. So let us continue. V of 2 is equal to, what is our x of 2? Of course, we have to copy this. 4, negative 1, and then 2. Again, minus. Okay, x of 2 transpose. So x of 2, we will transpose this matrix. So instead of writing it in vertical, we will write it in diagonal, because we are transposing it. So that would be x of 2, that would be equal to 4, negative 1, and then 2. We will have to multiply it with the value of v sub 1, which is also x of 1. So we have to copy it as it is. 2, negative 5, and then 1. Okay, and then on the denominator, v sub 1 transpose. So we have to transpose this one. Instead of writing it as it is vertical, we will rewrite it in horizontal. 2, negative 5, and then 1 times the v sub 1, 2, negative 5, 1. Okay, again we have to multiply it with our v sub 1, which is also our x of 1. So our v sub 1 is 2, negative 5, and then 1. Okay, using the properties in multiplication of vectors, so let us continue with the solution. X v sub 2 is equals to, copy this one, 4, negative 1, 2, minus, okay, we have to multiply this. Okay, first we have to multiply 4 times 2, that would be 8. Again, negative and then negative, it will be positive. 1 times 5 is 5, and then 2 times 1 is equal to positive 2. Same as true with the denominator. 2 times 2 is equal to 4. Negative 5 times 5 is equals to, both negative, it will become positive. 1 times 1 is equal to 1, and then copy this one here, 2, negative 5, 1. Okay, continue. V sub 2 is equal to, copy this, 4, negative 1, 2, equal to, we have to add this one, 8 plus 5 plus 2 is equal to 15. 4 plus 25, 29 plus 1, that is 30. Again, multiply it with 2, negative 5, and then 1. Okay, so let us proceed. V sub 2 is equals to, copy this, reference point, x of this one, the one that we are solving, 4, negative 1, 2. Okay, so simplifying it, 1/2, because 15 over 13 is also similar or equivalent to 1/2, dividing both the numerator and in the denominator by 15, so it will give us 1/2 times 2, it would give us 1. 1/2 times negative 1/5 is equal to 3 halves. And then 1/2 times 1 is equal to 1/2. I mean 1/2 times 5, that would give us yes, 3 half, and then 1/2 times 1/2 is equal to 1 over 2, or 1/2. Okay, this is 5 over 2. Okay, v sub 2 is equals to, we have to subtract 4 minus 1 is equals to 3, negative and then negative. Now 1 minus 5 halves is equal to 3 halves, and then 2 minus 1/2 is also equivalent to 1/2, I mean 3 halves. Okay, so now we already have our orthogonal basis. So this is our orthogonal basis. Okay, so we already have here a reference point a while ago, x of 1. Now we already have our orthogonal base, which is actually a base perpendicular to our x of 1. So again, the orthogonal base, this one, is now perpendicular to our x of 1. Now we have to solve for our orthonormal basis. Okay, so let us proceed. Allow me to write it here on the right side. Solving for orthonormal base. Okay, so first we need to find the magnitude of our vectors. Okay, so how we're going to solve it? The formula is the magnitude of v sub 1, okay, using this symbol here, is equal to the square of its component. The square of the square of its component. So that would be, we will use this formula here. Oh, that is negative 1. So that would be 2, this one, 2 squared plus, this is negative 5, and then we have to square it again. Okay, and then 1 plus 1, and then we have to square it again. Again, we are solving first for the magnitude of this vector. Okay, we are solving for the magnitude of this vector. So this is the formula. So the magnitude of v sub 1 is equals to, this will be equal to 30. Okay, magnitude of v1. So this is the magnitude of our v1. Now we also have to solve for the magnitude of our v sub 2. Okay, same formula. V sub 2 is equal to, so instead of using this one, we will use now our orthogonal basis. So we will use the components here, since this is our orthogonal base already. So that would be 3 squared plus 3 over 2 squared plus 3 over 2 squared. So the magnitude of our v sub 2 is equal to, this will be 9, 3 halves, so this will be square root of 6. Okay, now we already have our magnitude for our v sub 2. Okay, now we can proceed now for solving for the span of v1 and then v2. By the way, the span is actually, that means that is the distance between the two vectors. So we already have the vector 1 and then we also have the vector 2, so we will solve for the span of it. So how are we going to write it? Span is actually equal to w span of this one is equal to v sub 1 and then v sub 2. So we're writing it, the span of v sub 1, our v sub 1 is this one, 2, negative 5, and then 1. And then our v sub 2 is this one. So this will become 3 halves, and then another 3 halves. Okay, so that is the span of our vectors from vector 1 to vector 2. Now we can solve now for the orthonormal basis. Okay, so how are we going to solve for the orthonormal basis? So it's just easy. So we just have to divide the component over the magnitude. So the span, which is equal to b span, okay, that would be equal to v sub 1 and then v sub 2. So b is equals to span, what is our v sub 1 over the magnitude of v sub 1. Okay, v sub 2 over the magnitude of v sub 2. So that is the formula. Okay, let us substitute the values here. So v sub 1 is equal to 2. So we have to write 2 over v sub 1, which is square root of 30. Again, negative 5 over square root of 30. Again, 1 over square root of 30. And then our v sub 2, we will use now the values here. V sub 2 is equals to 3 over the component of vector 2, which is equivalent to square root of 6. And then the next one is 3 halves, or okay, 3 halves, 3 over 2 all over the square root of 6. Okay, and then another 3 halves all over again the magnitude of our vector 2, which is equal to square root of 6. Okay, so this is now our orthonormal basis. So just a wrap up for the solution. First, we have to look for the vectors, okay, as our guide here, x of 1 and then x of 2. Okay, x of 1 is equal to v sub 1 because we are referencing this vector. And then we will try to solve for the vector 2 since we are using the orthogonal base, or we are solving for the orthogonal base in reference to our x of 1 or v sub 1. Using this formula, okay, we will try to solve for the orthogonal basis and then the orthonormal basis using the Gram-Schmidt process or the Gram-Schmidt method. So this is how we do it. Okay, so I hope you were able to understand the discussion regarding the Gram-Schmidt process. Okay, so basically for the Gram-Schmidt process, we just have to solve for the orthogonal basis and then the orthonormal basis. So in this example, we only uses 2 vectors. Okay, but we can also use 3 vectors here by putting additional x of 3 here and then using the third formula for our x of 3, not the v sub 2. Okay, so it is already posted on our slide presentation. So if you have any questions regarding this topic, don't hesitate to ask me. Again, thank you and have a nice day.